Now we're going to examine some periodic trends. So trends, patterns in the periodic table. One of those is atomic size, how large an atom is. Well, how do you define the size of an atom? These are not marbles that you can measure with a ruler. They are a nucleus with these overlapping standing waves of electron waves / particles, right? How do you measure that? There's a number of different ways. You can look at what's called the non-bonding atomic radius or the van der Waals radius. And here we're looking at an atomic solid. Here we've got krypton in the solid state. And we're measuring the distance between adjacent nuclei. And we're going to say, well, the size of the atom then is, the radius is half the distance between adjacent nuclei. Because we can pinpoint, we can image where the nuclei are, so we can measure that distance, but we can't get a good picture of the actual atom. You can also look at a bonding atomic radius, also known as a covalent radius. So here you're looking at two atoms that are covalently bonded together. And hopefully it makes some sense that when these are covalently bonded together, they're going to get pulled closer than if they were just next to each other in an atomic solid. So here we're looking at, again, the distance between the two nuclei and the radius of the atom being half that distance. But this is going to be smaller than a non-bonding atomic radius. If we're looking at metals, then we're going to look at half the distance between two atoms next to each other in a metal crystal, because metals don't form covalent bonds. So if you measure atomic radius in different compounds, different atomic solids, you're going to come up with a variety of numbers for the radius. And so the most generally useful one is just an average of those. So what we're going to just call the atomic radius is an average radius for that atom based on its non-bonding radius and its bonding radius in a variety of compounds, just averaged together. It's a more general term. It's always going to be smaller than the van der Waals radius. We can use this atomic radius to give us an approximate value for a bond length. So the bond length, the distance between two adjacent nuclei, if we can look up the atomic radius for each of those elements, we can just say, well, the bond length is the sum of the atomic radii. So let me just draw a little picture here. So if I have these two atoms that are bonded together, I can look up the atomic radius for this one, and I can look up the atomic radius for this other one, and I can say that that bond length is the sum of the two radii. It's not going to be exact, but usually we just need to know approximately, and it's good enough. They can be measured exactly for that specific molecule, but most of the time we don't need that. Okay, so the trend in atomic radius. Part of this makes sense very easily, and part of it needs a bit of explaining. So if we look at atomic radius as you go down in a group, so this would be lithium, sodium, potassium, rubidium, cesium. These are all in group 1A, right? And so we see from this graph that the radius is increasing as we go down a group. It's not a linear relationship. We don't care. It's just increasing. And so we can confidently say that rubidium is larger than potassium. And this one does make sense because as you're going down the group, the atoms are getting heavier. It makes sense that they get larger. The real reason that they're getting larger, though, is that the principal quantum number is increasing. If you look at their electron configurations, the quantum number for the valence electrons is going up. right? And that corresponds to the period 1, 2, 3, 4, 5, 6. So cesium down in period 6 has its valence electron in the 6th principal energy level. Rubidium's is in the 5th principal energy level, right? So this is going to be further away from the nucleus than this one, the electron, and so the atom is larger. Yes.
Anything that's going towards FR, right, would be considered large?
Yeah, as you go down any of the columns, the atoms are getting bigger.
He's awesome.
We'll talk about the diagonal just now. Yeah. Yeah, starting with the easiest one. As you go down, they get bigger. Okay, yeah, that makes sense. So this next one doesn't necessarily make sense. If we look at this graph, here we have lithium to neon. So here are the noble gases, and we see as you go down the column for the noble gases that their size also increases. But between lithium and neon, this doesn't immediately make sense. Lithium is larger than neon. What? Why? I mean, lithium is only 6.9 grams per mole, and neon is 20 grams per mole. Neon is heavier, but it's smaller. There's a reason for this. And we see this pattern in all of these periods, right? Now these have some transition elements and things get a little wonky in there. So here's a different version of the periodic table where we're showing the size. So these are atomic radii, not atomic numbers, atomic radii in parts per million. Not parts per million, picometers, sorry. Ugh. So here's lithium, 152, neon's only 70. What happens as you go across the period, we are adding electrons into the same principal energy level. So lithium has its valence electrons in period 2. Neon also has its valence electrons in period 2. Well, that principal level 2 is still going to be roughly the same size. So then we might expect that these would all be the same size. So why are they getting smaller? Has to do with the shielding effect. So in a multi-electron system, we've got attractions between the nucleus and the electrons, but we also have repulsions between the electrons. So the outer electrons are farther from the nucleus and the core electrons are closer. And so the outer electrons, those valence electrons, are kind of having to look through the core electrons of the nucleus. The core electrons reduce the attractiveness. So shielding causes the outer electrons to not experience the full strength of the nuclear charge. So here we've got an example looking at lithium. So lithium has 2 electrons in the 1s sublevel and 1 electron in the 2s. So here's its 2s. This is going to be more on the outside. This is the valence electron, and we have these 2 core electrons. So the core electrons shield the nucleus for that valence electron. So when this valence electron looks at the nucleus, it's really seeing an effective nuclear charge of +1. And we learned about Coulomb's law that the energy, the amount of attractiveness there is proportional to Q1 times Q2, where these are the charges of the 2 species. So this is a -1 charge, and it's seeing an effective charge of +1 on the nucleus. You can think of this as these sort of negating or canceling out 2 of the protons in there. It's one way to think about it. I have this other weird analogy with clothing. So there's this really attractive girl, right? And You can see her in a bikini or you can see her in a parka, right? So which version is more attractive to the typical male? The bikini, right? Because you can see more of her. She's not as shielded, she's not as covered up. So these core electrons are sort of like clothing on a person. Of course, we could do the same thing with this really buff guy, right? And here he is in a Speedo, and here he is in, a spacesuit or something. Use your imagination.
Sorry, I was like, I don't like
Yeah, Speedos. So maybe just some cut-off shorts or something. I don't know. Whatever. You make up your own visual images. But you get the idea. This is like covering up the attractiveness of the nucleus. Okay? So effective nuclear charge, we can do a very, very simple calculation, and we say that the effective nuclear charge is equal to the actual nuclear charge, the protons in the nucleus, minus the core electrons. The core electrons are the ones that shield. The valence electrons do contribute, but they don't contribute enough for us to worry about them. So we're just going to go with the simplest explanation that works. So let's look at nitrogen and argon and compare their effective nuclear charges. So for nitrogen, how many protons are in the nucleus? 7, right? It's element number 7. That's not what I meant to do. We got 7 protons. And how many valence electrons do we have? What group is it in? It's in group 5. It's got 5 valence electrons. It has a total of 7 electrons because it's got 7 protons. Okay? So if it has 5 valence electrons, how many core electrons does it have? 2. Right, so it's got 2 core electrons. So if we are going to look at the effective nuclear charge, we're going to look at the actual charge in the nucleus, which is 7, and then we're going to subtract the core electrons, and we're going to end up with 5. Does that make sense? So nitrogen, 2 core electrons is, he's wearing a t-shirt and board shorts or something. Let's look at argon. How many protons does argon have? 18. How many electrons total does argon have? 18. How many valence electrons does argon have? 8. It's in group 8. 8 valence electrons, so how many core electrons? 18 minus 8, 10. Right? 10 core electrons. So the effective nuclear charge that's experienced by the valence electrons in argon is the actual nuclear charge, which is 18, minus the effective nuclear charge. Minus the core electrons. And so that gives us 8. So argon's outer electrons have this positive 8 attractiveness to the nucleus. Nitrogen's outer electrons have this plus 5 attraction. So which attraction is greater? The one for argon, right? So argon's outer electrons are more attracted to the nucleus. They're going to get pulled in tighter than for nitrogen. Yes?
What does the E stand for?
Core electrons. There's valence electrons, the ones on the outer level, and the core electrons are everything else. So let's go back to this picture. So we just looked at nitrogen, and we said that its effective nuclear charge was +5. What's the effective nuclear charge for neon? Neon is element number 10. So it's got 10 protons in the nucleus. And how many core electrons? 2 core electrons. 8 valence electrons, 2 core electrons. So its effective nuclear charge is +8. As we're going across this period from lithium to neon, we are adding electrons in the same principal quantum level. In the hotel, we're adding we're adding guests on the same floor of the hotel, right? So it's roughly the same size. But then for nitrogen, the attraction that those electrons feel for the nucleus is +5. For neon, the attraction is +8. +8's bigger. So neon's electrons are going to get pulled in closer to the nucleus because they're more attracted to the nucleus. Does that make sense? So that is why, as we go across, atoms get smaller. We're adding electrons to the same level, but the effective nuclear charge is larger, and so they're more attracted, they get pulled in. As we're going down, we're adding to higher and higher levels that are farther and farther out. And so they're getting bigger as we go down. Yes?
Group 8 is considered as the valence electrons.
Pardon me?
Group 8 is not considered the valence electrons.
Group 8 has 8 valence electrons,
Okay.
but it has 2, well, for neon it has 2 core electrons. How would I know? Because neon has 10 electrons total, and if 8 of them are valence electrons, the other 2 have to be core electrons. Or I could look at the periodic table and say, okay, well, all of these in period 2 are my valence electrons. How many electrons are above that? There's just 2, this one and that one. Any other questions? So I kind of already said this, but this is the quantum mechanical explanation for the trend. So as you're moving down a column, you're adding electrons to higher and higher principal quantum numbers. So those are going to have larger orbitals and thus larger radii. As you go across the period, your effective nuclear charge is increasing while the principal quantum number is the same. And so that increased attraction pulls the electrons in and causes the atom to be a little bit smaller. Now, for the transition metals, they are just less predictable than other things. Going down in a column, we still see a nice trend, but as you go across, it's much less predictable because we are adding core electrons as we are adding protons. And so the effective nuclear charge for all of the transition elements in the same period is roughly the same. So they don't really see a change in effective nuclear charge. And so they are roughly the same size. And so you are not expected to know trends across a period for the transition metals. So we should be able to answer questions like this. On the basis of periodic trends, choose the larger atom in each pair if possible. So if we look at tin and iodine, what we want to do is we want to find these in the periodic table. And so what I'm going to do is I'm going to draw a piece of the periodic table. So there's tin and here's iodine. They are in the same period. So what is the trend as we go across from tin to iodine? Is it getting smaller or bigger? It's getting smaller because the effective nuclear charge is increasing and the electrons are getting pulled in. So this one's smaller. That means that the tin must be the bigger one. You see how I did that? Okay, let's look at GE and PO, germanium and polonium, named for Germany and Poland. So here's germanium and here's polonium. So here we have things going on the diagonal. So going down, is it getting bigger or smaller? Bigger. So the trend going down would say that polonium is bigger. The trend going across, we said they're getting smaller. So going across says that germanium's bigger. These two trends are contradicting each other. So a reasonable answer here would be it's not possible to tell. If you were forced to choose, I would go with the downward trend, because adding to a larger level is probably a bigger influence than the effective nuclear charge increasing across. So I would say this one, tentative or not possible. I will not intentionally trick you with one of those on an exam. It could happen inadvertently, but I won't do it on purpose. Chromium or tungsten. So we have to find these on the periodic table. Cr over there and tungsten's below it. So these guys look like this. There's not G. Cr, and there's W. Which one's bigger? The tungsten. Because the trend is that as you go down, they increase in size. Any questions? These are trends. They are not always correct, but they're still useful.